presentation.
I hope I am audible and my screen is visible to all of you. Should I start?
Yes, sir.
Yes, sir. Yes, sir. Please proceed.
Okay. So good afternoon, everyone, once again. And my topic is geospatial data and its pre-processing. So in present time, the geospatial data is very important in different applications. For example, if we have to monitor the landslide, if we have to talk about flood mapping, if we have to go for deforestation or forest fire, if we have to talk about any of the other natural calamity, in that case, its analysis and its monitoring is very important, so that we could give a information to the actual position where these calamities has happened. So this is one kind of example. There could be many more applications that geospatial data can be used to give a proper information after analyzing those geospatial data. So if we talk about in recent time, the geospatial technology has developed by leaps and bounds, and we have got advancement a lot in this particular field. For example, if I talk about the spatial resolution, we have started in kilometers in way back when the satellite missions or this geospatial data formation was started. But today we are having data in the form of in centimeters. So from kilometers to centimeters, we have we have completed this kind of journey. In India also, we have in space matters, the space research Indian Space Research Organization has developed a lot. In one day, we have not only made a record of launching 105 satellites, but also we can convert any satellite into debris. With the help of ASAT, which are called as anti-satellites. So this is the development that we have seen in the space in the recent times, and we hope a similar kind of advancement will be there in the coming days also. So if I say the geospatial data, I request someone's mic is open if he can switch it off. So in recent times, we can also able to see such kind of progress and growth in this field. And if I talk about the geospatial data, one of the major sources of geospatial data is satellite. So first we'll discuss what is geospatial data and what should be the proper definition of it. So as geo means, we are talking about the earth, geo, and sometime the second thing is that the time factor will be related to that. So if for a particular time of distance, a particular time of span of time, if you're talking about a particular location associated with it, then we can go for a particular kind of analysis. So geospatial data is a time-based data that is related to a specific location on the Earth's surface. The location which we are talking about, it could be static or it could be dynamic as well. Static means if this static and dynamic totally depends on the goal or the kind of analysis we are going to perform. For example, if we have to find out the population of any district, any country, or any of the state, in that case, that location would be fixed. Suppose I'm saying I'm talking about the population of India. In that case, the location, the geographical location would be fixed, and that would be India in the world. But if I say the dynamic location, in that case, we are talking about some events, some natural phenomena which is not staying at a single position, but it is moving from time to time. For example, there are different kind of cyclones. So recently in 2020, Amphan was experienced by the coastal regions of Odisha and Kolkata. So in that case, the Amphan has started. It was having a source point where it has started, and after uh, the time passes, it was also moving towards the coastal area, and then it has entered into the entered in the some internal parts of the country. So in that case, if we talk about the geospatial data of the Amphan, in that case, it would be a dynamic since the Amphan's position was not fixed. So geospatial data combines basically two things: location information, any particular location, latitude and longitude can be described those locations, and then the characteristics of the object, event, or phenomena for which we are doing analysis, or for which the study is going on, or for which the data has been gathered. So if we talk about the data, data captures in GIS. So data captures, basically we are saying that we are talking about geographical locations. So whatever the biophysical materials are there on the earth, those should be gathered in such in with the help of some geometrical representations. For example, points, lines, and polygons. So points are used for those locations which are very small, which are too small, and they cannot have any area or any length. So in that case, we can use points. For example, telephone poles, wells, and electrical poles. They can be denoted with the help of points. Similarly, those elements on the earth, those features on the earth which are not having an area, but they are having a continuous structure. For example, roads, canals, so that can be represented with the help of lines. And those features which are having area, they must be represented with the help of polygons. So there are two data models which can be used to represent any of the geospatial data. So the first one is called as vector model, where we are only using point, lines, and polygons to represent different features on the earth. And the second one is the raster, where the data is in the pixelated format, means the pixels are used to represent the entire geographical locations, and each pixel will have any value between whatever the radiometric resolution of that image would have. So if we see here, there are three layers in the vector image. The first one is only we have used the lines to segregate the different boundaries of city A, city B with the country, and then we are having only lines to segregate the streets, and then we are having polygons and points to represent the parcels. Whereas in raster case, all the entire geographical area is divided into grids, and each grid is called as cell or pixels, and each pixel will have a homogeneous size, or it would have a similar area. The differences between raster and vector data is that if we talk about the approximator, as I have told you that in vector case, the entire area can be represented in the form of real numbers. Like if the area of any country is of any geographical area is 2.5 acre, then 0.5 can also be used. Means it can be in real numbers. But as we are talking about raster data, it is in pixel, and each pixel is having a distinct size which is in integer only. For example, if we talk about the Landsat satellite, it is having a dimension of 30 into 30 meter. Means one pixel, every time if we will choose a pixel from the image, it will represent 900 square meter of area. So in that case, this approximation error will be there when we are talking about the raster data. And storage in the form, if we talk about the storage capacity, the raster data will always require higher storage because of it is organized in the form of rows and columns in the form of pixels, and each pixel will have some data. So the storage will always be higher side for the raster, and the computational speed of the raster data will be faster to give the required information. There could be different examples of the geospatial data, but in this presentation, we are only focusing on the satellite data or raster data, because we are talking about the pre-processing of the geospatial data which are available or which is provided by the satellites only. So there could be different also that I have mentioned here. Spatial analysis. So as I have discussed that for different kind of natural calamities like landslide and others, we can go for a geographical location, and for that location, we can find a particular or fundamental kind of information. For example, if a flood is coming, then we can calculate the area that in the entire state or entire district, how much area is affected by the flood, and what are the other area that are flood prone. So for that we can do analysis. So those processes where we are talking about the location, attributes, and related features in spatial data through overlays and other analytical in order to address a question or gain useful information is called as spatial analysis. So in spatial analysis, the geographical location must be there so that particular information or knowledge can be extracted through that through a particular study. For example, there are two scenarios that I'll discuss here, and I'll show which one is spatial and which one is not spatial analysis. For example, if I have to calculate the average income of any group or of any company, then it will not be a spatial, because we are not talking about the location. If I'm saying that the average salary of software engineers or average salary of teachers, then it is just representing a community, not the spatial or the geographical factor. But in the second case, we are talking about the United States population. In that case, the population will be of United States only, and that United States is a country and it has a geographical location. It is having a latitude, longitude, and that is bounded by a boundary also. So the very first kind of spatial analysis that was done by Dr. John Snow in London. So he has performed a study on the cholera patients in 1854, and he had made a clusters on the basis of geographical location, and then he has described which area is having more patients and which are having less patients. The second one here, the color is used to denote the population of the different regions. The darker region will have a higher side of the population. So these two are the examples of the geospatial spatial analysis, and geospatial data has been used here. So stages of spatial analysis, there are 5 key stages. First, you have to understand the goal, that what kind of analysis you are going to perform and what is the geographical location that you have chosen for your study. Then we will talk about the different data sets that could be available, whether it could be GPS data, it could be other GIS data, or it is a satellite data, it is a drone data, or other statistical information that is available, that is related, that is available associated with that particular location. Then we have to choose the tools, methods, or techniques which can be applied over the gathered data to give the to perform the analysis. Then in the final case, we will choose the method, or we will implement to get the result, and final result will be analyzed. So as I told that in geospatial data, we will talk about satellite imageries. So if I talk about satellite is a moon, planet, or machine that orbits a planet or a star. So it could be any device, it could be any satellite, could be any device which is revolving around any other device in the space or object in the space. So Earth and Moon, they are the natural satellites, and similarly we can have man-made satellites which can be launched in the space, and they can revolve around any of the certain planet in the space, and they can keep tracking of that particular planet which has been focused for the study or focused for the application. So whatever I'll discuss one very interesting concept that was introduced by Newton in his Cannonball Experiment. So in Cannonball Experiment, he was using gunpowder and he was filling it into his cannon, and he was firing a ball. So after with the energy of gunpowder, it was covering some distance and then it was falling. So as he was increasing the gunpowder, its strength, the power, the energy the ball was getting, it was also increasing. So after a certain period of time, when the energy is extended from the from the gravitational scope, then it has started revolving around the object where it was. So this experiment is also is a fundamental concept behind the satellite motions, where the circular motion of the body object, if it goes beyond a particular limit, then it is called as escape velocity and it start revolving around the object because it leaves the gravitational scope of the that particular planet. So here we have discussed in the first figure, you can see the Cannonball Experiment. In second case, we can see the different forces that are there on the ma'am, Ganga ma'am. Hello, am I audible, Ganga ma'am? There was a warning
Yes,
prompt, ma'am. There was a prompt window which was showing.
okay, so everyone, everyone will rejoin if the meeting disconnects. Okay.
Okay.
So you carry on, sir, please.
Okay.
Thank you.
So this is the anatomy of a satellite. There are different factors, there are different components, and after combining those components, we can form a satellite. And on the basis of the height of a satellite, we are having three different kinds of satellites. Low Earth orbit satellites, which is having a height of 2,000 kilometer. And at 10,000 kilometer, we are having second kind of satellite, that is medium Earth orbit satellite. And on more than 36,000 kilometer of height, there is a third kind of satellite, which are called as geostationary or high Earth orbit satellites. So we have understood that satellite is providing the geospatial data, and how it is providing. So it is totally depending on a phenomena that is called as remote sensing. So remote sensing is a phenomena through which the satellite senses the object or the feature which is there on the Earth or on the planet, and after its reflected energy, it is capturing the information. So if I go to the basic definition of the remote sensing, remote is the existence of something at distance, and sensing is the phenomena of acquiring or perceiving. So remote sensing is an art and science of getting information about any object, phenomena, or method through a device, and that device is not at all in contact with the object, phenomena, or method, and it is giving or acquiring the information about that thing. So if I talk about the human senses, there are 5 human senses, and out of these 5 human senses, 3 are basically working on the principle of remote sensing. For example, smelling smelling is the procedure which is working on the remote sensing. The hearing and the sighting, these first 3 are I have shown in the diagram. These first 3 senses are working on the principle of remote sensing, whereas the taste and touch, they are depending on they are not at all following the remote sensing procedure for acquiring the information. So for remote sensing, we are having 4 major components that should be required: the illumination source, platform, sensor, and instantaneous field of view. So in this figure, the entire remote sensing procedure has been described. The sun is the natural source of the electromagnetic energy, and here it is the illumination source. So electromagnetic energy travels through the atmosphere on the Earth, and after that, this energy can be transformed into 3 different forms. Either it will be absorbed by the features, or it will be reflected, or it will be refracted. So whatever the amount of reflected energy is there, that is the basic, or that is the main source for the geospatial data. So that reflected energy travels back in the environment and reach to the sensors, which are either carried by any of the airborne or spaceborne sensors, and those sensors are capturing this reflected energy, and further this reflected energy is converted into pictures by analog to digital converters. So this is the entire phenomena of remote sensing. So after that, this is one picture. So there is sensor, different art features. The satellite, it is from the sun or from the illumination source, the different energy, the electromagnetic energy falls on the earth, and it is reflected back to the sensor, and then after sensor captures the reflected energy, it is giving the pixelated information, and those pixelated informations are forming the entire pixels, entire image. So if I talk about the electromagnetic spectrum, there are different kind of energy. The electromagnetic spectrum is divided into different subspectrums like visible, infrared, microwave, radio wave, ultraviolet, X-rays, and gamma rays. And the sensing ability or the sensing capability of different features is also different. For example, the sensing capability of human is entirely different from the dog or any of the amphibian or any of the other creatures. So whatever the RGB color we are able to sense, the similar sensing property is not there for other creatures. So for different creatures, the world seems differently because of their eye sensitivity. In sufficient light, the eye works as a multispectral sensor, and because of that, we are able to see the colored images or the color of the different objects. So blue, green, red, basically it is having 300 nanometer to 400 nanometers or 0.3 to 0.4 micrometers, and green 0.4 to 0.5 and 0.5 to 0.6 micrometer range of the electromagnetic spectrum. And because of this visible light, 0.3 to 0.6, we are able to see different color properties of the different objects. So similarly, this electromagnetic spectrum is also the basics for the formation of satellite images, which is used by different satellites in the space. So on the basis of electromagnetic spectrum, there could be three categories of satellite imageries: the panchromatic, multispectral, and hyperspectral. I'll discuss from here the electromagnetic spectrum, that what is panchromatic, multispectral, and hyperspectral. Suppose this is the range of electromagnetic spectrum from 10 to the power 3 meter to 10 to the power minus 5 nanometer. If this entire range will be treated as a single range, then only one image will be captured, and that will be called as panchromatic image. For example, if I say that there is a satellite, and its sensing ability is in the range of 0.3 to 0.6, means 0.3 micrometer to 0.6 micrometer, that is visible range only. So in that case, it will capture the image, or it will capture the reflected energy which was reflected back in the range of 0.3 to 0.6, and with the help of it will generate the image. And if 0.3 to 0.6 will be treated as a single spectrum, then a single image will be possible. So in that case, it will be called as panchromatic image. But if 0.3 to 0.6, if it is divided into three subspectrums, and I can say that there are three sensors in the same satellite, and 0.3 to 0.4 will be captured by one sensor 1, 0.4 to 0.5 sensor 2, and 0.5 to 0.6 sensor 3, then it will be a multispectral, because a single range will be divided into three different subspectrums, and each subspectrum is now handled or dealt by a different sensors. That will be a multispectral. And the hyperspectral is a more advanced one, where we are not talking about 2 or 3 bands, but we are talking about 100 and 1000 sub ranges of the spectrum. So if 0.3 to 0.6, I say that 0.3 to 0.31, 0.31 to 0.32, 0.32 to 0.33. So 0.1 difference, we are having more than 30 30 subspectrums. So, and each subspectrum will be allotted to a single sensor, and that sensor is now capturing the information or reflected energy in that range only. Then it would be a hyperspectral, because its range is become more narrower. So on the basis of this, we are having three categories. Panchromatic, only one image would be there, only one range, only one sensor would be there for one range, and multiple sensors will be there for range when it is divided into subspectrums. So multispectral and hyperspectral, the same range is having multiple subspectrums, and that subspectrum is having different sensors to dedicated sensors to collect responses. There are now we'll talk about the satellite image resolution. So there are four different kinds of resolution that a satellite image could have. The first one is spatial resolution. So spatial resolution is only is all about the dimension of a particular pixel. If a pixel is there, then we are saying that its spatial resolution would be 30 by 30. It means that horizontally and vertically its dimension would be 30 meter. So one. So I was there on satellite image resolution. So if I talk about the satellite images, they are having four kind of resolutions. The first one is spatial resolution, which talks about the pixels dimension in horizontal and vertical length. So if 30 meter is there, if you are saying the 30 meter is spatial resolution, it means that vertically and horizontally it is covering 30 meter of geographical area on the Earth surface. So 900 square meter area of 900 square meter of area will be covered by this particular pixel if it is of 30 meter spatial resolution. So spatial resolution is nothing but the area covered by a particular pixel on the Earth. The next one is spectral resolution. As I have told you that for the electromagnetic spectrum, if we divide the ranges of a spectrum, then it could give you the spectrum. Subspectrum. So for example, here 0.5 to 0.7, there are four different subspectrums that can be used for the imaging. There are a fifth one also, and there is a sixth one. So for this entire, if we are talking about any particular satellite, then its spectral resolution will be 6, because it is able to sense, or it is able to capture images information into these ranges of the electromagnetic spectrum, and not be able to gather information in those ranges which is not defined here. So this range will not be entirely used for any kind of sensing. This will also not be used, and after 6 it will also not be used. So possibly the spectral resolution of the satellite would be 6. The next one is radiometric resolution. Radiometric resolution is defining the number of bits required to represent the intensity level of the image. So more the number of bits, more the radiometric resolution. It means that we are having more information. We are able to discriminate more colors. For example, if we are having green band. So in green band, if we are having 10 bit or 20 bit, then 10 bit is not able to, it will have a coarser radiometric resolution, and 20 bit will have a finer radiometric resolution, and we are able to discriminate within the colors also. So radiometric calibration is defining the range of the intensity or gray level. More the bits, more the gray levels, and more the discrimination between the features. The next one is the temporal resolution. So temporal resolution is talking about the time period or the number of days after which the same geographical location will be followed by the satellite. So here I have shown one figure where the same image, the first satellite is talking about the same image, and after certain days it is passing through the same position, same image will be generated. So generally, for example, if I say Landsat 8 is one satellite which is having 16 days of repeatability, means temporal resolution is of 16 days. Means if we are talking about, if I say that greater Noida image, greater Noidas or greater Noida's image is generated today, then just after 16 days, we will again have the image of Greater Noida without any geographical distortion or any other distortion. Same image would be there. So geospatial database, here I have shown different attributes: the satellite name, its type, number of bands, band's name, resolution, and its availability from the time when it has started and from the time when the mission has ended. So Landsat 5, 7, 8 resource set with advanced wide field sensors, resource set with list 3 sensors, Sentinel 2, Cartosat 2, multispectral scanner MSS, Landsat 1 to 5, Landsat 4 and 5, enhanced thematic mapper Landsat 7, and then Landsat 8 and Sentinel 2. So these many satellites I have taken care, and I have talked about the different bands, its resolution, and its time period when it is available, and also the different kind of possible resolutions. So now the next part of the geospatial data and its pre-processing, that is pre-processing. So whatever the satellite imageries that are that is provided by the different space agencies, like for ISRO, NRSC, National Remote Sensing Center, is one of the only the organization which is providing images. So whatever signals, whatever the raw information the satellites are providing, those informations are converted into images by NRSC only. So these images will be provided, and directly we cannot use these images. We have to pre-process it. We have to bring it into a form that is suitable to our goal. Means whatever we have intended, whatever plan we have made, that we have to go for such kind of study, then according to that study, we have to pre-process the data. So there could be a data format that there could be different challenges, different pre-processing that we could do. The first one is data format. We want data in different format, and the format provided by the agency is different. So we have to bring it into a format that is required. So georeferencing system, we have to georeference, means if the geography, if only the image is provided and its locations are missing, then we can go for the georeferencing. Map projections, data resolutions. We will talk one by one about these pre-processing techniques, and after pre-processing only we will go for the final analysis for this geospatial data. So the first one is that I have talked here, conversion. Pre-processing involves the format conversion. This is a very standard task which we have to do on regular basis. For example, if analog data is there, we have to convert it into digital. If there are different processing tools like ArcGIS, GIS, QGIS, ADAS, NV, SNAP, all these processing tools are having different kind of formats. So for example, if SNAP has been used for the generation of the image, then then its format would be different. And if you want to process with ArcGIS, it is not possible. But these kinds of conversions are there. These kinds of the different kind of tools are there through which we can convert one format to other formats. Basically, I am using NV or SNAP. These are the two tools for the pre-processing, and the format conversion is possible through these tools also. Like the format, the TIFF is there. From TIFF, we have to convert GeoTIFF. The image, the IMG file is there. We have to convert into PNG, or PNG is there. We have to convert into TIFF. Then all these possibilities are there. So format can be converted from one to another. The next one is data reduction. Data reduction, it means that whenever we are downloading data, this downloaded data is covering a larger area, larger geographical area. And suppose I have to work on a smaller area, then processing the entire image is not convenient and not logical also. So from the entire image, I have to extract, I have to crop that particular part which is required to me only. So that can also be possible here. We can reduce it. So there are the 4 ways through which we can crop the image, through which we can extract that particular portion which is of our use, and we can skip or ignore other portions which are not required. So the first one, image, we will select the image. There is a rectangular box. We can choose that particular area and we can skip others. if we are having map, we can overlay the map on the entire image, and also we can extract the image. If we are having some other image file, suppose I have processed one file and it is there with me, and I want to extract only those area which is available in the file, then also I can extract with that. And if it is not, if any of the three options are not there, I can create my region of interest, and on the basis of region of interest, I can also extract the or reduce the image, or extract my area of interest. For example, here, like if I use to download the Landsat 8 imagery, it is showing this much of area, and the rectangular box, the region which is there in rectangular box, it is showing the Hawaz region, and these are other regions. It is covering more than 5 or 6 districts. So instead of processing the entire image, I have extracted my area of interest, and it is in the right. I have shown it this area. So this process is this pre-processing is called as area image reduction. The next one is mosaic or merging. In mosaic and merging, basically we are if the area of interest, suppose this is the area which I have extracted. Suppose if half of the area is available in one grid, or like this is one area. After this, in right also there would be image, in top also there could be one image, in left also there could be an image, and bottom also there could be image. Suppose if area is below this, then, or if in the rectangular box, if half of the area is coming into one tile, and the next half of the image or right half of the image is coming into the next grid, then the area of interest will be in two different images or two different tiles. So we can reduce the images from the two tiles, and then we can merge it. So I have shown here that this area, this much, the left portion is extracted from one tile which is available, and the right picture is taken from some other grid. And then after we have used the mosaic tool to merge these two different images and form a larger area, or to make the area of our interest. So basically, if we are having multiple, if our area or area of interest, if our study area is larger in size, and if it is not available into a single grid, then we can go for this mosaicing tool, and we can merge from the different sources and create a single file. Then the next one is georeferencing. Georeferencing, sometime the images provided by this agency, it is not georeference, means latitude and longitude informations are not available, they are missing. So in that case, we can use any of the pre-processing tool like Snap or NV to georeference. So how we can georeference the data? There are 3 steps. There are 3 different methods. Image to image. Suppose I have an image from different satellite and it is georeferenced. Then I can use that image to georeference that image which is having missing latitude longitude information. So image to image georeferencing is possible. Image to map georeferencing is possible, and also we can collect ground control points with the help of GPS and some other devices, and those ground control points can also be used for the georeferencing purpose. So here we have used ground control points to georeference the 2 images. The next one is layer stacking. Layer stacking is basically useful when we are dealing with the multispectral imagery. In multispectral imagery, multiple images would be there with respect to different spectrums, and all these images can be combined together, can bring together after this layer stacking process. So suppose I was saying that if I talk about the visible range, there are 3 ranges RGB. So RGB in R range 0.5 to 0.6, we are having different image. For 0.4 to 0.5, we are having green range and it will have different image. And for 0.3 to 0.4, we are having blue range and it will have a different image. But if we'll apply this layer stacking process, these 3 different images will be converted, they will be combined, one after another, and like first image will be there, the next image will come, and the next image will come, and it will be layer stacked, and a single image will be formed. Then geometric corrections. Geometric correction. There is a distortion in the images acquired by the Earth observation system cannot be transferred because they are geometrically distorted because of the errors in the satellite positioning in its orbit. The fact the Earth is turning on its axis as the image is being recorded, the effects of relief, etc. They are so geometric correction is required because of the displacement of the because of the displacement of the satellite from its orbit. It may have a different like whatever the exact location would be there, or for that particular pixel it was not giving it, and some 0.3 or 0.5 meter of error will be there. So that error can also be removed with the help of geometric correction. Then the next one is radiometric calibrations. So radiometric calibration is done to convert the digital number into the actual reflectance value. Like whenever there is a problem like azimuth and elevation, atmospheric correction such as fog or aerosols or sensor response is not proper. In that case, instead of converting like whatever the Earth features, they are reflecting the energy. It is not reflected from the surface of the Earth, but it is reflected from the top of the atmosphere. So this top of the atmosphere reflectance is not of our use because we are not able to find the strength of different features, in terms of reflected energy. So it must be bring down, and we should have a bottom of the atmosphere reflectance so that actual or real reflectance can be observed. So radiometric calibrations is done to get the bottom of the atmosphere in terms instead of top of the atmosphere, and also we can say that digital numbers can be converted into the reflectance values. So radiometric correction is classified into the following three types: radiometric correction of the effect due to sensor sensitivity, or sun angle and topography, or atmospheric corrections, atmospheric conditions. The next one is image interpretation. So image interpretation, it is possible for the multispectral images, and that can be done with the help of two different aspects, two different procedures. The first one is true color composite, and the next one is false color composite. So composite means we have to combine multiple images. So true color means there are three channels for the color formation: red, green, and blue. So if red, green, blue channels are there, and actual range of RGB is passed to that the grids or the channels, then we will have a true color composite. For example, 0.3 to 0.4 is blue, 0.4 to 0.5 is green, and 0.5 to 0.6 is the red band. So in electromagnetic spectrum, if whatever the image is there in the 0.5 to 0.6, it is red band only, and if it is passed to red channel, and similarly for green band, for green channel we are passing the green band, and for blue channel we are passing the blue band, then it will be a true color composite because true colors are passing to the respective channels. But also it is possible from red channel we can pass blue, from green channel we can pass blue, or from blue channel we can pass the third one. So in that case, it is not true, but it is false. So that is false color composite. So in true color composite, we'll have a basically we are doing it for the visualization of the image, that in which image, in which combination, which color is getting, which feature is getting enhanced. So here I have shown one image, and out of, like as I was saying, that for blue, see the blue is here. Blue 0.48 means it is coming in 0.4 to 0.5, or average value would be taken. Green 0.5, and red is 0.65. So if this red is passed to this is, there are in the selection band, in the band selection, there are in the band selection here, there are three channels: red, green, and blue. So in red I have passed red, in green we have passed green, and in blue we have passed blue. So it is forming the true color composite. But in false color composite, instead of red, I have taken short wave infrared 1, for green short wave infrared 2, and for blue I have taken an imagery captured in NIR, and we have generated a false color composite. Here also we can see that for red we have taken SWIR1 in this selection selection parameter, and in green we have taken SWIR2, and for blue we have taken near infrared, and this is false color composite. And if we compare the two images, the color visualization for different features is entirely different. So basically, for different combinations, we can have different images, and maximum we can have unique only one true color composite image. And for false color composite, we can have if NCR -1, where N is the total number of available bands, and R is 3 always, because 3 at least we have to require. So NC here in case of 7C3, we are having maximum 7 images, and out of 7 images we can create combinations with 3 by 7C3 -1, and this many number of false color composite can be possible. And one more aspect is there, separability analysis. So separability analysis is focusing on the concept that how different features are separable into different spectrums. So for that we are having transform divergence and Matsuda Jeffreys Matsuda distance. On the basis of these two factors, we can find the values, and we can say that in this particular combination, these features are more separable. Here I have taken different combinations. This is the part of my research also, and I have shown that there are 5, 6, 7 are 3 different imageries. So 5, 6, 7 combination, 5, 6 band combination, 5, 7, and 6, 7, and we have talked about 5 different earth features: water, sand, water, land, water, vegetation, urban. So 5 features: water, sand, land, vegetation, and urban. And we have checked that in this particular combination, which feature is more separable as compared to the other one. So we can also check the separability of features in different combinations, and also in different combinations. So these are the few topics which we have covered in the pre-processing of the geospatial data. And after pre-processing, we can go for the final analysis or the implementation of any of the method or classification or prediction or any other application which is suited for the study. These are the references that I have used for this presentation, and thank you everyone. Thank you for your patience, and if there would be any question, I will be.
Thank you, Dr. Mishra. So if the participants are having any questions, they can ask.
Yes, I have a couple of questions, if it is possible.
Yes, sir.
My name is Mukhtar Nasirov. I'm from Samarkand State University. I'm interested on the software, what you use for remote sensing. What type of software you use?
Sir, there are a number of softwares that are available for this purpose, and there are open source and there are paid softwares also. So if I talk you about the open source, there are, I will suggest you to note it down. There is Snap, 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 and Google Earth Engine and QGIS. So these are the 3 softwares which are widely used by the researchers for the different purposes. So Snap is a European Space Agency software. It is totally free of cost, and it is a very advanced and a powerful tool for the geospatial analysis.
Okay, if it's possible, one more question. So you mentioned about the radiometric correction or like this. It means that you can eliminate the noise like dust, clouds, etc. Is it possible to use this one?
Sir, yes, sir, it is possible because I have used NV software, environment for visualization.
Oh,
and there is a radiometric corrections, that option is there, and radiometric label or reflectance label and thermal label, there are 2 options. So for OLI images, we are using this reflectance label corrections, and after that, it is possible to convert it into bottom of the atmosphere reflectance.
Because there was a lot of discussion about the usefulness of remote sensing in the dryland areas. From the dryland areas, I work on the monitoring vegetation cover in the grasslands. So in our area, Uzbekistan, we have semi-desert areas, or dry areas, so a lot of.
Sir, your voice is breaking in the middle, and you are not.
So I think that we're using this type of means for calculation of indexes, different indexes of vegetation cover, like NDVI.
Okay.
Normalized different vegetation index. So some people argue that it's not true because in drylands it's dusty area, so dust may influence negatively to the real data. So what do you think about this?
Yes, you are very much correct that we can propose different kind of indices, and I have also proposed. I have worked on the water bodies, and I have proposed 2 indices: open source water index and MPWI water index. So, and it is only possible with the multispectral data. And whenever we are applying these kind of indices for the multispectral data, we have to be very sincere, and we have to be very careful while choosing the threshold value. So once we are able to decide the threshold that beyond this or under this water body or vegetation is there, then we can easily decide. So choosing a threshold is a critical and very crucial task.
So thank you. My last question is, so still it's possible to use a drone with images for remote sensing calculation, or how is applicable drone images?
Drone images can be used, and there are a number of places. Like I went recently, I visited to IIT Roorkee, and there people they are using drone images. And my future plan is also considering this portion where I can use or where I can apply or generate my own images for this kind of analysis. So drone images, yes, they are having a good scope, and in future I hope one very good advantage with the drone images is that we are not having a limitation of the temporal data. Like for satellite data, we have to wait for 5 days or 6 days or 16 days as per the repeatability of the satellite. But for drone, whenever we have to require, we can fly our drone and we can capture the data. So it is having a very good scope, and in future, most of the people or the remote sensing people will consider this data as a good scope.
Okay, thank you so much. I sent an email to your email box. If you will have time, please check your email. And
yes, I have shared my mail
ID.
If there is anything we can discuss, we can collaborate, and I can answer that.
I hope we can keep in touch. Thank you very much for your presentation.
Thank you.
Thank you.
So any more questions? Anyone?
Yes, I have one question. Good afternoon, everyone. Thank you for seminar, Dr. Vikash Kumar. I have interested in these spatials. You did good seminar on image recognition systems. I have 2 questions for you.
Yes, sir.
First, how does your concepts of zoning of in geosystems different from sensing method your purpose?
I was unable to hear you properly, sir. Can you repeat?
How does your concepts of zoning in geosystems different from sensing the method your purpose?
I'm unable to understand, sir. Can you write your question to me?
You know zoning algorithms?
Zoning?
Yes, zoning.
I'm not aware of it, sir.
Yeah, I understand. You use only...
Could you repeat in Uzbek? I will try to translate it into English together.
Yes. Esh Habiba. Men bu kishiga aytmoqchimanki, siz geotizimlarda o'sha zondlashtirish algoritmlarining qaysilaridan foydalangansiz? Bu sizdagi algoritmingiz bilan qanday farq qiladi? O'zi aytgan hozir.
Zondlashtirish algoritmi.
Yeah.
So, Dr. Mishra, so he wants to ask that what is the difference between your algorithm for zonding, for geospatial, from other algorithms or other methods or other techniques?
My algorithm, I haven't shown any algorithm here. As per I have just discussed the pre-processing techniques that are used for pre-processing any of the satellite data. If you are having any of the satellite data, these are the major things. But I am talking about the optical. If we go for the synthetic aperture radar data, that is SAR data or microwave data, in that case, these steps will be changed because there could be speckle noise that we have to deal. There could be geometric. There could be different kind of geometric, like it is capturing images in the slant form instead of perpendicular angle. So azimuth is different in SAR and optical. So the strategy of pre-processing is entirely different for both the scenarios. But I guess I have not shared any algorithm. These are the basic techniques of pre-processing which we have to follow whenever we are talking about the optical data, optical satellite imagery.
Okay, thank you, Dr. Mishra. So do you have other questions? Or should I translate into Uzbek?
Yeah, I understand. Don't need translate.
Okay. So
Thank you for
If you have any question like related to algorithm and that I was not able to explain, you can write me. I can also respond to your mail.
Okay.
There is a communication barrier also. Your language is not suitable to me.
okay.
Anything else? Any other queries?
So dear colleagues, do you have any questions?
Maybe no questions.
Thank you very much for a nice presentation.
Okay. Thank you, Dr. Mishra, for your helpful and fruitful presentation. It was nice to us.
Thank you. Thank you, ma'am.
Thank you.
Okay, thank you everyone for joining. And I would now request everyone to please turn on your cameras so that we can have a photograph, group photograph. Thank you.
Cool.
So, Dr. Vikash, you can unshare your presentation.
Stop sharing. Yes, ma'am. Just a minute.
Okay. Everyone, please turn on your cameras. Thank you everyone for joining, and thank you Dr. Mishra for sharing this very interesting topic with all the participants. And the last thing for the day is that we have Teachers' Day here in India. So for all of you, to all of you, it's Happy Teachers' Day from our side. Thank you all for joining.
Okay, thank you very much.
Thank you very much.
Thank you, everyone.
Bye for now. Thank you all for joining.